what we need to get up to speed on. And I'm gonna be honest with you guys, I'm putting a lot of pressure on myself to try and make this make sense and try to find the level of depth that you guys even care about. And I mean that wholeheartedly, because this just spirals deeper and deeper and deeper down into some pretty intricate depths. But I was reassured as I just sat in a terribly boring business development webinar with Jamie and Sarah and Bud Meyer and a few others, and they were talking about all the terms that we're talking about here today. So as we get into this, and you're like, a neural network, machine learning, deep learning, supervised data, all of these bingo card of terms, I'm reassured that even on a business development side, they're talking about this is what agencies are talking about, these are what clients are talking about, these are what partners are talking about. So my challenge to you today is, however you soak up information, one, I hope that I'm going to communicate it in a way that makes sense, but two, I hope that if it's taking notes, then it's taking notes, or if it's coming back to the recording of this presentation later, and then so be it. It's agency education for a reason, and that a lot of stuff is going to be new, and you're going to have to learn it. And there's not going to be a test, but your test will be talking coherently in your discipline meetings, talking coherently with your teams when you're brainstorming different ideas, when you're talking with clients. So it's the onus is on you to say, do I care enough about this to like understand how machine learning is different than deep learning? Which sounds super technical, I get it. But that's where our industry is headed. And I'm telling you, it'll become more common as time goes on. So my job here today is to give you an overview of the landscape. Where we will end up today, I'll talk about that here in a little bit. But essentially, I'm just showing you how all this stuff comes together and the terminology that's appended to it. A little bit about how it works, a lot of capabilities and limitations and what makes it up. But in a second session, when we get to agency education part 2, that's when I'm going to be able to show you guys various tools within generative AI that I think you'll actually use. And we'll talk about input prompting. We'll talk about prompt engineering. We'll talk about what makes good prompts in order to get inputs that are better outputs. We'll get into tooling, which is eventually into 5. But today is, how does this whole ecosystem work together? And a lot of it's going to be new. So the roadmap that we've been on has kind of been like this, right? This is how generative AI is going to work at LNet. Well, you guys know that we've talked about ethics and where your guys' role is, and where AI cannot, what it cannot achieve, and where you guys need to supplement. So you guys know that. We've also talked about the approach. So once you feel confident about AI, how it works, and you feel good about your tool set, what's in your toolbox, you'll know how to use it and where it's appropriate to use it. So this is where we've been, but where do we need to go? We need to get into the knowledge, the foundational part. So buckle up, bear with me, let's try and do this together. It'll be tricky, but we'll get through it. Let's ask good questions, let's have good conversations, and eventually we'll get into the apps like I mentioned. So if you guys are gonna go learn about AI, this is kind of a very simplified version of the landscape. I hate these charts. I hate these charts. Jamie, at the last meeting, there was a very simple chart and it showed how AI was going to work with your data lake and your DAM and your CDPs and all of the good stuff. This is usually how it's presented, which sucks. And then it gets into this. And then it gets a little bit more into math and statistics. And I personally chose a super blurry one because I hate it. I really do. And so I'm going to kind of reshape this hopefully in a way that is very easy for you guys to understand. And when I say this, my disclaimer is, as we learn how these technologies work, the biggest takeaway for you all is you need to understand how they work, much like how the car sort of functions, before we can do some test drives. Back to that analogy from the very, very first session that we had. This will ultimately allow you to say, why am I not, when I'm trying to use these tools, how come I'm not getting what I need out of them? Well, you're probably doing something that's not intended to do. So that's not the way the technology works. And so that's the point of today when we get through jargon and when we're deep into that kind of thing. There's a very layered approach to all this. Here's another graph that I hate. And you'll see, to get to something like ChatGPT, which I use that because it's low-hanging fruit, guys. It does a disservice to the rest of the landscape. There's some pretty impressive tools out there. ChatGPT is of course one, but that's what you hear in the headlines, so I use that often just for example's sake. But to get to that, you have to understand the rest of this. And so that's why we're going to talk about the rest of this, and we're going to arrive at ChatGPT at the very end of the session. So to start at the very large layer, that's the AI realm, right? We talked about AI as the process of making things smart. What I need to communicate to you all is that not all AI is the same. And if you heard Dr. Griffiths at the Lookout talk about capabilities of AI, she had similar slides. People slice and dice this in different ways. And it's based kind of on two different things. How capable it is, so how sophisticated it is, and then what it's intended to do. So its functionalities. And the best way that I can kind of personify this is to talk about people. So if Joey is my first AI, Joey, where are you? You're right there. Okay, Joey's right there. I will make you stand up. But Joey is narrow AI. Joey, what can you do?
I can write.
You can write. Okay, cool. You're pretty good at writing. You're really good at writing.
I'm a copy machine.
You're a copy machine. You are a copy machine. Unfortunately, you are a weak AI, but you are a copy machine. Can you design?
No.
You cannot design. Okay. Can you help create audio segments and clips?
No.
No.
I'm weak.
You're weak. But you can do what?
I can write.
You can write. Okay. So narrow AI is AI that can simply do one limited task. Now, limited is kind of a misnomer because he's really impressive when he writes, but he's intended to do one single thing. My next example is going to be, I got to figure out who I tapped just yesterday. Luke. Where's Luke at? Hey, Luke. Luke is some pretty impressive AI. Luke is strong, right?
Hell yeah.
Very, very small AI. Now, look at him. Luke, you can write copy, right?
Oh yeah.
So you can do what Joey can do.
Yep.
General AI. But you can also do a few other things, right? You can do design.
Yep.
You can work with audio. You can work with natural language processing. You can do a lot of things. You can do it just as good as the rest of us, right? The rest of us humans.
Yep.
Yeah. So general AI is doing to the level that we all can. Each one of you is very dynamic. You can talk about weather, then you can talk about sports, then you can talk about doing these different things. And you do it good enough. No offense. You do it good enough, right? You know all these different areas. You do it to the level that we can today. Now, super AI. Kelsey Frost. What up, girl? You are super AI, right? What can you do?
Well, Travis, I can flip better than Simone Biles, paint better than Michelangelo. I can also write songs better than the Taylor Swift,
Oh,
and analyze a lot better than Kelsey Frost.
oh, and you can see this the stair step pattern here, right? Joey can do a single thing, do it pretty well. Luke, general AI, can do multiple things, but only to the level that of quality that we have. Kelsey, the Frost, can do this exceeding beyond Taylor Swift, Simone Biles, and any of our other examples. Now, that's based on capabilities. Switch over to functionality. I gotta think of who I had for this Masters, right? Reactive machine. So an example of what Masters is, he's the chess master, right? Masters is a chess AI that can figure out the next move, right? It can react based on the situation. Now, if we asked him to do absolutely anything else, he cannot do it. He is meant to simply react to a very simple string of inputs, and that is what Eric is. Limited memory. Sarah Waldner. Wow. What up, girl?
Really?
I mean, I didn't pick limited memory, she picked limited memory, okay? Sarah, what are you?
I'm a chatbot.
You are a chatbot. You're a chatty Kathy.
Yeah.
When is my package going to work?
Your package will arrive in 3 days. Here's the tracking number.
Okay, excellent. Now, oh, yeah, go ahead. 3 weeks later, 3 weeks later. I come back and I say, hey, Sarah, that package, remind me what was in it. I've been ordering a lot of packages.
I don't recall. What is your order number?
You can't put it together, right?
No.
You have limited memory.
Yeah.
The scope of your memory was based on that simple interaction we had the very first time. Limited memory. We can learn from the situations and improve Sarah so she can get a little bit better, but in the moment, she cannot do that. See?
Dory?
What up?
Yes. Dory? Yeah.
Dory, a little bit of Dory. Good example.
Oh.
All right, next up, theory of mind. Sydney. Hello, Sydney. You are very impressive. You can do reactive machine. You have a good amount of limited memory, but what's unique about you? You can understand what?
I sense out the vibes. I can feel your emotions. I can sense what you're feeling and predict based on respond accordingly.
The difference between Sarah and Sydney is Sarah's programmed to talk to me about my package. One is gonna all those good things. She can't tell that I'm pissed. She can't tell that I'm angry about it and sense my emotion based on how I'm talking or how I'm typing. Theory of mind is what Sydney would be because she can help pick up on some of those social cues, if you will, EQ type of things. And then lastly, self-aware, Mr. Van Dismount, where are you at?
Rare.
What are you? You are,
I can tell that you can feel, and that makes me feel.
there we go. This is the Terminator shit. This is the stuff that people, the sci-fi type of thing, right? Now, the point of me going through all these is that we live currently, presently, in today with only these 3 segments of AI. We have narrow AI, we have Joey, right? He can write and he can do it really well, ChatGPT. We have reactive machine, like Masters, can beat humans with chess simulations because it knows the calculated moves. Limited memory, we have Sarah, we have chatbots, right? This is where we are today. We are not yet in the era of anything else. So let that set the stage for a little analogy that goes the wrong way. I think I have some slides out of order here because I have a slide that says a little analogy goes a long way. But welcome to my mid-journey created onion that has layers that happens to represent AI. What did you say?
Why is there a slide?
Why is there blood? I don't know why there's blood. It's concerning. But there's like a process. Oh, we like ripped the chip out of it. I don't know. This turned cannibal really quick. This is those crappy graphs that I showed you earlier, really fuzzy and blurry. This is me reincarnating this, and hopefully this is a little bit easier for you guys to understand. Notice the layering. Now, there's some use of color here, but you can see it's very intricate that there's subcategories, there's categories, subcategories, subcategories of subcategories, and further on down. When we finally reach that dark gray, we will have arrived in the conversation for today at generative AI. And that's where I want to split part 1 and part 2, is that next time we'll get into ChatGPT and how it formulates the sentences, and it'll be really fun to look at that. But for right now, I want everyone to understand how we even get to there. Because generative AI is at the very end of this train. And that's where all of these tools that you probably have people talking about on the internet, or you see them on social media, that's where we will arrive. So that's the onion. That's my slide. That's a great way out. But let's start at the top. So do we feel like we have a foundational knowledge of what AI is, and that we are in the era of narrow AI, weak AI, I suppose. No offense to Joey, but remember back to the very first session, think of it as like the word technology, very, very broad. That's why it's the biggest layer. It's the process of making something smart, okay? I get really upset when people say, that's AI, that's AI, that's AI. Now, you should be able to walk away today and know, well, that's actually just like machine learning, not actually AI, or that's here nor there, right? So a sub-discipline of AI is machine learning. Machine learning is going to use data, statistics, and then a series of trial and error and feedback in order to optimize tasks. We use a lot of machine learning here today. We'll talk about what that looks like, but the goal of machine learning is to try to make things better and mimic a very automated process that we would be able to do as humans ourselves. Machine learning, very, very broad. Machine learning was primarily developed based on kind of that conditional type language. Are you guys familiar with conditional formatting or conditional logic, which is if this decision, then go here. If this, then that. If this, then that. It follows this very, very rigid process, rules, okay? Rules. This is called explicit knowledge because it's literally programmed to do if this, then that. If you look at code on a website, this is going to probably be really hard, but what's highlighted there is if. And if that condition is met, it's going to execute a function. This looks like Chinese to you guys, right? Because you don't work in code. Maybe Carl's the only one that really understands this. Well, what does this give you? What is this accurate snippet of? Our website email. If button is clicked, perform these options. If input is formatted incorrect, then supply this feedback answer. Success, or try again, or not strong enough, those types of things. So that my example here is to show you that this exists today, the explicit knowledge, and it does perfectly fine. Like machine learning is doing what it needs to do in order to understand people trying to convert on our website for an email form. Where machine learning gets really impressive, where we've gone beyond saying the code needs to be this equals that, and if this, then that. Machine learning can do a lot more than that. It can mimic the goals of what we're trying to do with automated processes, but it has three main components. And this is where I hope you guys start to kind of tag on to some of these principles. Machine learning needs three things for its recipe, and we'll go into each of them. When you have those three things, you will have this crazy looking diagram here, and we'll eventually get to what that is. Right now, I'm going to call that a neural network, okay? But machine learning needs those three things. When it's doing that, when it has those three things, here is what we can do in everyday life. We can use text to speech. We can predict the weather. We can forecast things. Your inbox hopefully works pretty well in understanding what's spam and phishing and what's a regular good email that we want to receive. Autocomplete the next word. Navigate the fastest route. Or what I think is what blew my mind is machine learning is the principle of medical detection right now. It can look at scans, feedback labs that we have, and say, based on that pattern, that coincides with someone who has this type of, hopefully not a disease, right? But this type of condition, right? Machine learning is what powers all of that. So machine learning is really, really impressive. That's my overall goal. But did you guys catch, for like the 800th time, what is the recipe? Three things: the type of data, the algorithms it's using, and how much computing power is involved. This is where we start to get really deep. So bear with me. Traditional machine learning, those examples that I showed you, the medical imaging, the medical translation, speech to text, weather forecasting, that is in the realm of traditional machine learning. Notice how this is orange. Traditional machine learning, this is its recipe. It's going to use supervised data. It's going to use either or maybe both, two different types of algorithms. One called regression, one called classification. Lastly, it's going to be able to do this, but it's not going to be overly taxing on the machines that it needs to run. It can do this in low computing environments. That's important as we move down, because if I go back to my slides, notice that little phrase over there, the race for quantum computing. Anybody that works on the DSU account, you're hearing a lot about quantum, right? What can we do with quantum? We need to get to that level of computing, because as we get more intricate here, and we go further down the funnel, or the onion, I should say, you need more powerful machines to do the things that we think are really cool or really impressive. So traditional machine learning, traditional is going to be this recipe. So talking about the components of that recipe. Supervised learning. Now, this is probably like the most text heavy slide that I have. I'm blurring out the right side because as you guys know, these are they kind of nest underneath each other, right? And so machine learning is technically both things from the onion example, but I want you to focus on traditional machine learning. That's using supervised learning methods. Now, this is all statistics. This is all math. If you guys wonder how your Facebook feed works, algorithms, math, right? Some of you might be English majors, design majors, the arts. You're gonna have to understand a little bit about that. These are all using mathematical principles. And in a supervised learning, AKA a structured learning environment for traditional learning, for traditional machine learning, those are going to be labeled and categorized. Very clean data sets. You typically own these data sets because you've marked the data to say this equals this. When you have that, you will have higher accuracy from that data that you have, your model, your training model, and you can do better at applications for predicting and forecasting things. Bear with me here. So, what does supervised learning look like? Let me use an example. Don't get caught up in like facial recognition. That's not the point of this. Usually these are like a zebra looks like that. An apple looks like this. I used us because I think it's fun. What is a FIPSI? Well, if we labeled that is a FIPSI, that's a FIPSI, that's not a FIPSI, that's not a FIPSI, and we were to give an input into our supervised learning model, that will be able to recognize, because we've labeled our data really cleanly, it can understand and it's been trained to know that if I give it that, its reaction will be FIPSI. Go ahead.
But this like also applies, so in your example of like our email form on our website, like an email address is a something @ something. Like that would also be like what we would train in supervised learning, like this is an email, this is not an email, if it's just an @ sign with nothing on each side, for example.
Correct.
Okay.
Yep. So that's the data, supervised, and we'll eventually get to unsupervised structured. You're gonna hear these terms quite often. What is ChatGPT built on? Technically a little bit of both, and that gets into a little bit something different, but structured data works really well in those fields or those examples that I talked about. What algorithms does it use? Here we go. Math. Who did well in math in college? I won't look for hands. I'm waiting, Kelsey. That was only one, two hands. Rachel? Okay, cool. This is where we get into the types of models it does. And I couldn't care less that you guys really remember, well, machine learning uses the classification algorithm. Well, I know what I say it, that kind of thing. No, that's not the point of this. It's to show you that when people build these applications, developers, they're very statistically savvy. They use those types of things to help sort the data in a way that runs the back end of these applications. So you can quite visually see how that looks. What's easier probably for you guys to understand is if I use examples, okay? So healthcare, those patient outcomes that we talked about, if you have all of these, all of this data, you would be able to see, well, this is what cancer patients typically look like. These are the levels of non-cancer patients. When you put in someone's data, you'd be able to use a classification algorithm. The machine would be able to understand, well, more than likely, to a statistical probability, this could be a case of that happening, right? Other use cases that are using supervised learning. The biggest thing here is they're using the supervised learning or the structured data sets. Real estate, if you know how many bedrooms, if you know the area, the location, this is great for predicting what's your home value. Zillow does that, right? For those of you that just scour on the internet like I do for property all the time. That's how it comes up with those things. Traditional machine learning methods. Finance, how do you predict what the stock price is? That's machine learning, right? Structured data, because all of that is really cleanly organized. Lastly, it can do these in low computing environments. We talked about that a little bit. It only gets harder, more challenging, and more computationally demanding from here. So when that's less computationally demanding, this is where you get into we've had traditional machine learning for a while. And it's been relatively affordable to use. As we eventually get into unsupervised learning, which is getting into generative AI and those principles, notice how it costs a lot of money to pay for some of those tools. They have subscription models, they have usage tiers. They have to find a way to offset a lot of the costs that are needed to run these types of algorithms. So to kind of take us back to that crazy little diagram. Traditional machine learning, your recipe is three things, right? And that is supervised data. It's using one of two algorithms, classification or regression, and it's using low to moderate computing power. You bring all of those together, you have what they call in this industry your neural network. You love neural networks, don't you? So here is what your neural network looks like. We're going to talk about this a little bit, but essentially your neural network is how it all comes together and it helps receive your inputs to formulate your outputs. So let's not go there. Let's try and switch this over a little bit and give you like an example. And I'm well aware that Zoomers, you might not be able to see this example because I just flipped to my iPad to be able to walk through it, but bear with me, I can send you the example when we're done. So hopefully this all kind of works together. Bear with me. Simple neural network, right? This is what you guys see. So if we want to build machine learning to accurately tell if we need to hire interns for the summer, here's how we would do it. We would say, okay, what do we want our inputs to be? Well, those questions could be, will they save us time? And I'm sorry for my terrible handwriting on iPad, and it's usually trash anyway. So save time. Now we may ask, will they be self-sufficient? Okay. And lastly, will they save us money? Okay. Okay. So those are our inputs, right? Now in coding world, you have that's our x1 value, that's our x2 value, that's our x3. We have to say yes or no. Binary is ones are yeses, zeros are nos. So will an intern save us time? Yeah, they're really good at that. So that's a 1. Will they be self-sufficient?
No.
No. Thank you for the feedback. Will they save us money?
Yes.
They will. They're going to cost us money, yes, but we can't. They're also going to provide value, right? Okay. So in our simple neural network, that is part of our inputs, and those x's are kind of that hidden layer number 1. It's our values, right? So this is kind of like over here. Sorry, I kind of went left to right, changing room to a girl, but then we can say, how important are these things? We're building this machine learning model. Well, hold on, I need to get this out of here. Okay. So we need to weight it. This is our weight of the 1, this is our weight of the 2, this is our weight of the 3. Well, how important is our time? Really important. Our threshold is going to be 5 for the values here on the weighting system, which we'll use later in our threshold. But let's just say, well, my time is the most important thing. So 5. Them being self-sufficient, us hiring an intern, we know that they're going to take training and coaching and mentoring. So let's just say that's 3, right? And lastly, will they save us money? That's the yes and no thing. Let's just say that's 2 because we know we're going to pay. Okay. Now, we use y hat. Essentially, we're going to take this and multiply it all together. So 1 times 5 is going to be 5. 0 times 3, math means 0, thank you. 1 times 2, 2. Now, I mentioned that our threshold is 5 for our weighting system. So if these are our y hat values, we sum those together. So 5 plus 0 plus 2, what does that equal? 7. And before we get to this final stage, when we talk about our outputs, we are essentially saying positive means, yeah, hell yeah, let's hire them. Negative means, hell no, we're not gonna hire them. So that's our output layer. Now, 7, which is our y-hat, minus our threshold, that equals 2. That is our answer for saying, that's like us creating, is there a disease? Or is this a good stock price, right? If we need to use traditional machine learning to hire an intern, this is how we would use a simple neural network in order to do that. We have an input layer. We have developed our own systems for the hidden layers, and then we can achieve outputs. The reason that it's called a simple neural network is because it has, let me flip back here. The reason it's called a simple neural network is because it only has 2 hidden layers and it's done. Okay? Let's peel back the onion a little bit further. Inside of machine learning, if we're no longer talking about traditional machine learning, we're now into deep learning. The only difference there is what's used in the recipe and the type of neural network that that recipe uses. Notice how this one is way more complex. The rule here is that there is no amount of hidden layers. There's no limit to the hidden layers. You can build as complex of a model as possible. Think about ChatGPT, how it organizes in weights words to figure out what creates a good sentence. I have no idea how many hidden layers it uses in its deep neural network to be able to do that. It's not as simple as our intern example, right? So if we're thinking about what deep learning can do and why that's much more complicated and using a complex neural network, now we get into things that you guys really know and love in your everyday life. The algorithm. How many people have heard someone say, well, my algorithm gives me this, and your algorithm does that? It's true, right? It's not like the worst phrase in the world. I penalize people for using terminology differently in other areas of AI, but essentially, think about the example that we went through in the neural network of how it's weighting all of your interactions. It's tagged in a way that however many hidden layers that they have, it can create and say, this is good content, right? Smart assistants do this. Facial recognition. The biggest thing with deep learning, it's so much better at understanding patterns. And that's the overall goal of any machine learning, is pattern recognition. But deep learning is more impressive because of the extended amount of hidden layers on the inside of the model. And you can get these types of examples in real life. So if we look at, this is the regular recipe, right? This type of data or these types of algorithms or this type of computing power, deep learning is using these. Darker orange, deep learning is using unsupervised data. It's using clustering or association algorithms, math, and it's using very, very heavy computing power. Now, the difference here, notice how I've revealed, not a great reveal on the right side of the screen. You've seen what supervised learning is on the left side. Now you see what unsupervised learning does on the right side. This has not been labeled. This is a mixed bag of everything. The best example I can give you here is, because people talk about like, well, where does ChatGPT come from, right? What's its information? It's using web scrape, backdated to like, I think it's 2021, September is the last time that the model was trained and deployed. It's using that data, that's web data. Think of how messy the internet is. It's not organized. It's not categorized to say, this is what a social media site is, and these are the interactions. This is what Wikipedia is. All of that information. It leverages unsupervised learning and creates patterns and recognizes them to create new combinations. Back to this example. We don't label what is a FIPSI, okay? We say, here's people. And you figure out who the employees are, right? And it can figure out, I'm seeing 3 distinctive employees, okay? Let me give you another example. If you guys are, if you're familiar with DALL-E, or you're familiar with Midjourney, those are text-to-image generative AI applications. What they're saying, they take all of Rembrandt's art, all of Picasso's art, and they say that artist typically designs or clusters these, there's a pattern here, right? It typically looks like this. That way, if you say, draw me this in the form of Rembrandt or Picasso or whatever, it can say, well, I'm going to group together pixels like this. Here is your image, right? And you've seen how people can make new art in that way. That's unsupervised learning at play. It's using the different algorithm structure. It's using clustering and association. I don't think you guys really care about what those actually look like. So let me just flip it to the next slide. That's looking at data about a customer, but figuring out how you can personalize recommendations or target media in a different way because it found patterns in how somebody's journey online reveals itself. It figures out all of those clusters of they're more likely to do this. It's not explicitly said with similar to like a regression algorithm predicting the next thing, it's finding its own conclusions. Image compression, it can figure out what are useful pixels to make the image look really nice and associate that with the larger full scale image to say, does this degrade what the image is trying to show? No, I can remove these pixels. That's how we compress an image. Lastly, computing power. This is why there's like kind of the nuclear arms race for quantum. Definitely more computational demand. And that's why it costs a lot more to do these things. Putting it all together. Traditional machine learning on the left, we walked through that, has its time and place. You'll hear a lot about people saying, well, why would you always use deep learning? Well, now you guys understand that costs a lot more money. That's a lot more complicated. And it's a lot harder to have all of that unsupervised data because you typically don't own it, okay? Machine learning works perfectly fine for all of those use cases when you need the outcomes, right? What people usually do, or what people in this industry usually talk about is, are you overprescribing? If this takes so much time and effort, why would you, and you can receive the same results, why wouldn't you use traditional machine learning? So that's kind of the argument in those developer communities. If you followed along through what AI is, all of the 7 different types, right? As we personify them, what machine learning is, the classification of finding patterns, and then being able to use those in a different way. Understanding what deep learning is as it differentiates from machine learning, we will have finally arrived at foundation models. We're here, a new term, and I'm kind of out of breath talking about all these things, so I'm going to have our little nerdy guy from IBM explain foundation models, which essentially feed into an LLM. He'll talk about what an LLM is, but think GPT.
GPT, or Generative Pre-trained Transformer, is a large language model, or an LLM, that can generate human-like text. And I've been using GPT in its various forms for years. In this video, we are going to, number 1, ask what is an LLM. Number 2, we are going to describe how they work. And then number 3, we're going to ask what are the business applications of LLMs. So let's start with number 1, what is a large language model? Well, a large language model is an instance of something else called a foundation model.
Onion.
Now, foundation models are pre-trained on large amounts of unlabeled and self-supervised data, meaning the model learns from patterns in the data in a way that produces generalizable and adaptable output. And large language models are instances of foundation models applied specifically to text and text-like things. I'm talking about things like code. Now, large language models are trained on large data sets of text, such as books, articles, and conversations. And look, when we say large, these models can be tens of gigabytes in size and trained on enormous amounts of text data. We're talking potentially petabytes of data here. So to put that into perspective, a text file that is, let's say, 1 gigabyte in size, that size can store about 178 million words. A lot of words just in 1 GB. And how many gigabytes are in a petabyte? Well, it's about 1 million. Yeah, that's truly a lot of text. Now, LLMs are also among the biggest models when it comes to parameter count. A parameter is a value the model can change independently as it learns, and the more parameters a model has, the more complex it can be. GPT-3, for example, is pre-trained on a corpus of actually 45 terabytes of data, and it uses 175 billion ML parameters. All right, so how do they work? Well, we can think of it like this. LLM equals 3 things: data, architecture, and lastly, we can think of it as training. Those 3 things are really the components of an LLM. Now, we've already discussed the enormous amounts of text data that goes into these things. As for the architecture, this is a neural network, and for GPT, that is a transformer. And the transformer architecture enables the model to handle sequences of data like sentences or lines of code. And transformers are designed to understand the context of each word in a sentence by considering it in relation to every other word. This allows the model to build a comprehensive understanding of the sentence structure and the meaning of the words within it. And then this architecture is trained on all of this large amount of data. Now, during training, the model learns to predict the next word in a sentence. So the sky is, it starts off with a random guess. The sky is bug. But with each iteration, the model adjusts its internal parameters to reduce the difference between its predictions and the actual outcomes. And the model keeps doing this, gradually improving its word predictions until it can reliably generate coherent sentences. Forget about bug. It can figure out it's blue. Now, the model can be fine-tuned on a smaller, more specific data set. Here, the model refines its understanding to be able to perform this specific task more accurately. Fine-tuning is what allows a general language model to become an expert at a specific task. Okay, so how does this all fit into number 3, business applications? Well, for customer service applications, businesses can use LLMs to create intelligent chatbots that can handle a variety of customer queries, freeing up human agents for more complex issues. Another good field, content creation. That can benefit from LLMs, which can help generate articles, emails, social media posts, and even YouTube video scripts. There's an idea. Now, LLMs can even contribute to software development. And they can do that by helping to generate and review code. And look, that's just scratching the surface. As large language models continue to evolve, we're bound to discover more innovative applications. And that's why I'm so enamored with large language models. If you have any questions.
So, to kind of look at this entire conversation, for part 1, we've essentially arrived at foundation models. When we get into part 2, we're going to look at how these generative AI applications work based on what they are. So ChatGPT being a large language model, computer vision, that's essentially Google image search, right? Think applications like that. Generative adversarial networks, that's what the GAN is, and then multimodal networks too. So we will get into the tool set in part 2, but I wanted to make sure that we arrive in the ecosystem and understanding what some of these buzzwords are, so you can start to talk about those when people talk about AI. So I'm sure that there are several questions. I'm going to skip past that. That's a wrap just for today. Look forward to any dialogue that we have. Sarah, thank you.
Okay, I have 2 questions.
Yeah.
First one, is machine learning always have 2 hidden layers between the input and the output?
A simple neural network always has only 2 layers, which is usually traditional machine learning applications.
Okay. Second question is, the onion is not a Venn diagram, correct? Like, it's not like, because deep learning and machine learning, like you know what I'm saying? Like, doesn't mean this is all.
Machine learning, or sorry, deep learning is machine learning, but machine learning is not deep learning, right? Right. Think of deep learning as a subset I said deep learning, right? Think of deep learning as a subset of machine learning. So there are other applications, but when you have those complicated deep neural networks with all those different layers to be able to do things like transformers, like you saw when you talk about a large language model, that's the more intensive application. Now you're using deep learning, which is machine learning, but it's deep learning. It's-
Kind of like a peer.
Does that make sense?
Yeah,
Like,
kind of,
you're kind of following with me?
Yeah. Okay.
There's no dumb questions with this, guy. This is the first time you've seen it. Like, I studied research papers about this, and I have to reread them like 100 times. But
Can you go back to the, neural network
Sure.
diagram? Oh, yep. So in our example, we only had 3 little circles on our hidden layer and not 4, but all of these have like 4. Does that
Yeah.
mean anything?
that does not mean anything.
Okay.
That's meant to show you that there is a multi-relationship, or like, yeah, these could be so tall. What those are called are nodes, and you can build your architecture based on a million different nodes. It moves spirals from here, guys. This is like trying to give the too long didn't read version of all of this. But great question. Yeah, like it's not fixed in 3, 4, 4 all the way across. This is meant to show you that the amount of hidden layers can be hundreds, thousands, millions, and that's to essentially equate to, that just means that you have a very complicated model, so it does really impressive things. That's why we have DALL-E and Midjourney and Adobe Firefly and all of those different things, because they're using very complicated, deep neural networks, not as simple as my intern example.
So like can supervised learning have multiple hidden layers or just 2? I think those stairs.
So when it's deep learning, that means that you are using unsupervised data. So it is going to take that data and send it through the neural network, and there could be as many different layers or complications as needed to achieve the outlook, or the outcome, sorry. I don't know if that necessarily answers what you were looking for, but
It just looks like supervised learning is like a little more chill. Or like there's only 2 hidden layers, like is that in every example or is there like 3, 4, 5, 10, 20?
always 2.
Okay,
That's why that's number 1. Number 2, this can be hundreds if need be.
okay.
It can be as simple as 5, if that's what the tool needs to do.
So is supervised learning always with a simple neural network?
Yes,
Okay.
and it will use a classification algorithm. Because it can do these 2 types of things. It can find a trend line to say you're here or here, a positive or negative value. What we use, I should have mentioned this, when we did that intern example, when I did the simple neural network, we used a classification algorithm. That weighting that I did, that's a classification algorithm. Because what did we say? Negative value is a no, positive value is a yes. If we did that simulation 100 times, we'd have plots everywhere, right? Depending on what our inputs were and what our questions were. But that's why this works, is that you can receive that output. Think of the weather. If you're doing weather forecasting, it's plotting forecast, historical data. It's going to help you arrive at what is the weather going to be next Thursday. Well, it should be 78 degrees based on the pattern of data that it's following, right? And it can do that relatively simple with a simple neural network to get that done.
And if it was a strong AI, it could say the weather is gonna be nice because it's 78 degrees. But Alexa can only say the temperature is 78 degrees. She doesn't say it's gonna be a beautiful day, Sarah. You're gonna love it, right?
Well, generally I would say, here's the weather, but I'm gonna make you a packing list for today.
That would be-
And then, here's your playlist to go along with it, and then, you should stop and get gas at this gas station, like it's pulling it, it's doing multiple different feats within one. These algorithms cannot handle that.
No.
That's why we don't have generalized AI at this point. It's going to be a version of deep learning because it's going to have to find its own conclusions and then do crazy association
Yeah.
to combine things and do different things. We're not there yet. We're still in narrow AI. But thank you for taking it back to the beginning too, because if you guys have questions about the types of AI, those exist as well.
Back to the intern example, can you explain like the 2 that we came out, was that on the way to 5? So like, or can you just explain that final conclusion?
So
Like, what does the 2 represent?
the 2 is the value, and we had to say yeses need to be of these values and nos need to be, we need to equate it to decisions for us, right? So we use the rule of thumb that positive is yes, negative is no. So if we went through all of this, and we said that, will they save us time? Hell no, it's -5. Okay, let's see if I get my math right. 1 times -5 would be -5. We'd end up with a negative value, right? That would ultimately sway our decision to say no. We should not. do
So
that.
just the fact that it's a positive number means yes.
Correct. In this verse, it's a very rudimentary example, but yes. Try to keep it 1s and 5s. Good.
So is the hidden layer 1 the binary step, and then hidden layer 2 is like our ranking?
Good question. Yes. Yeah. I should have lined it up, but I was afraid I'd line a little over here.
So
So
what
we're here and there.
equation did you say we're using for this one?
That's regression, or sorry, classification.
Classification. So in classification, is the hidden layer always binary, the first one, or is it what you classify? Like,
It's what you would classify it as.
Okay.
I use binaries as yes and no's just to get this answer.
okay, cool.
Sorry for the handwriting. Well, so be, especially when we have to do that. But unfortunately, Zoomers can't see my iPad,
Dang.
so it's tough for them to.
Okay, so question on this screen, can deep learning use both of these algorithms?
Can deep learning, yes. So I didn't want to complicate a very convoluted subject. Technically, here we go. Technically, there's 2 other types of learning. There's semi-supervised learning and there's reinforcement learning.
Please stop.
Yep. You're trying to find that right level pretty well. There's a lot of examples, okay? Yeah, I mean, this is like, it's very easy to say black and white. To give you an example, ChatGPT is actually using semi-supervised. It's using a little bit of structured data. It needed that in order to create its model, but primarily using unsupervised learning to perform its actions that it actually does. I didn't want to create more bubbles for you guys. Go ahead.
Would you say that supervised learning only works, or like structured only works with like human input, and then like unsupervised, unstructured can work without human touch? Would you say that's correct, or?
There's the same amount of human interaction, but it's at different steps.
Oh.
So I'm really glad that you mentioned that. I think a talking point that I missed here was because supervised learning was intended for predictions and forecasting, you have a lot more manual human work upfront. Data hygiene, you have to get it. I mean, you guys know, like, how can we upload lists? How do we organize our data? That's where all of your work is. But if you have that done correctly, it is going to be more precise and have higher accuracy in a supervised learning environment. Conversely, you can just feed it unsupervised data, right? No manual actions needed on the front, but then what do you need? Tuning and fine tuning and quality assurance on that data to try and organize it in a way and fix what it couldn't conclude on itself. It's a greater risk and it's faster because it can just pull it all in. You don't have to use manual effort to be able to make that happen, but there's going to be more error there. That's when you get into, have you guys heard about hallucinations with AI? That's when you get into hallucinations because it takes more fine tuning to it. So your efforts on the back end versus on the front end with supervised learning.
It's like that crazy Twitter example that person was, remember that there's like They were saying me.
Yeah, Kay or whatever her name was.
Yeah, was that like unsupervised?
That would have been deep learning, unsupervised data. Because it was reacting to comments. And it was seeing new information in real time, so it had to create its own associations to provide responses. It didn't have a finite script to be able to output responses. Like, that's the best way I can sort of answer that, but that would be deep learning,
Not a chatbot.
not chatbot.
And all this is narrow AI, right?
All narrow AI, great point. We're getting. Yes, that is, top layer of the onion, there.
Narrow AI, yes.
We're here. Specific tasks, most of the AI that surrounds us.
Specific tasks.
All right, 1 o'clock, thank you all for your time.